So, this area maxima minima is very important, and in this area we need to have an understanding of what critical points are, we need to know the definitions of local maxima, local minima, global maxima and global minima, and we need to look at application of derivatives in applying derivatives to find local maxima, local minima, global maxima and global minima. So, we will be dealing with these three areas of understanding what critical points are, and we need to know the definitions of local maxima, local minima, global maxima and global minima, and we also need to know how to apply this application of derivatives, the concept of derivative, to find local maxima, local minima, global maxima and global minima. Let us look at the definition of critical point. Critical points are the points which belong to domain of the function. First and the foremost condition is these points, they belong to domain of the function, at which the function is either differentiable but derivative is equal to 0, or the function is non-differentiable. Critical points are points which belong to domain of the function, where the function is differentiable and f dash x is equal to 0, derivative is equal to 0, or the function is not differentiable at all. Let us look at the graph of sin x between 0 to 2 pi. Now, between 0 to 2 pi, each and every number along the number line from 0 to 2 pi, everything belongs to domain of the function. So, everything in the first look is capable of being derivative of the critical point of the function. Now, critical points are only points on this graph where the function is non-differentiable or differentiable but derivative is equal to 0. Y equal to sin x, we know it is a differentiable function. Y equal to sin x is differentiable on R. So, we will not get any case of non-differentiability on this graph. So, only hunt should be for critical points where derivative is 0. Derivative, where is it 0? Slope of the tangent is 0 at x equal to pi by 2, and it is also 0 at x equal to 3 pi by 2. So, there are only two critical points from 0 to 2 pi for the function y is equal to sin x, they are pi by 2 and 3 pi by 2. So, to find critical points, we need to identify those points in the domain at which the function is differentiable and derivative is equal to 0, or the function is not differentiable. Let me just give you an understanding of this critical point with the help of a graph. Let us draw a function whose graph is this way. Let us say this is 0. Let us say abscissa of this point is 3, 4, 5, 6 and 7. So, we are looking at a function whose graph is given from 0 to 7 here. Now, critical points on this function are the points which belong to domain. Each and every point from 0 to 7 is part of domain of the function. We can see graph stretching itself on the entire range of 0 to 7. So, each and every number between 0 and 7 is part of the domain. Now, among these points where either the derivative is 0 or the function is non-differentiable, these points we call them critical points. So, are there any points where the function is non-differentiable? we can see a sharp point here, and this sharp point indicates non-differentiability. So, this is one point of non-differentiability. So, 3 is a critical point, 3 belongs to domain, and at this point function is not differentiable. 4 is also a sharp point, tangent slope from left hand side, we can see some negative number, from right hand side it is almost close to 0. So, we have a sharp point here at 4. So, 4 is also a critical point. There is no other point of non-differentiability. Everywhere throughout we have points of differentiability. And then let us see those points where the function is differentiable and also derivative is equal to 0. It is differentiable between 0 to 3, but nowhere derivative is 0. Nowhere derivative is 0. Derivative is 0 at this point. We have a tangent parallel to x-axis. So, at 6 we have another critical point because derivative here is 0. So, we have only 3 critical points, 3, 4, 6, all of them belonging to domain. 3 and 4 are critical points because the function is not differentiable at 3 and 4, and 6 is a critical point because we have derivative equal to 0 at 6. So, in order to find critical points, we have to check for the points of non-differentiability or the points at which derivative is 0. Then let us look at the definitions of local maxima and local minima. A function y is equal to f of x is said to have local maxima at a point x equal to x naught if and only if f of x naught is greater than f of x for all x belonging to deleted neighborhood of A. Deleted neighborhood of x naught. A function y is equal to f of x is said to have a local maxima at a point x equal to x naught if and only if f of x naught is greater than f of x for all x belonging to deleted neighborhood of x naught. We are using deleted neighborhood of x naught because there is no equality here, and this is very important that there is no equality here. F of x naught should be strictly greater than f of x for all x belonging to deleted neighborhood of x. In the just close vicinity of x naught, just around the neighborhood of x naught, let us say this is the point x naught, we can see f of x naught, y coordinate at this point, is more than the y coordinates at the surrounding points. Just observe this carefully. Y coordinate at this peak point is much bigger than the y coordinates at all the surrounding points. So, we say because f of x naught is more than f of x for all x belonging to deleted neighborhood of x naught is a point of local maxima. Let us look at another graph where we can see which are the points of local maxima. Let us say there is a graph of a function which stretches from 1, 4, 6, 10, 8. Let us say this is 2. So, we have a graph of function stretching from 1 to 10. This is the graph. Let us see which of the points from 1 to 10 qualify to become a local maxima. Now, any point somewhere in between 1 and 2, let us see if it can be a local maxima. At this point, we understand the function value, it is y coordinate of this point. Just in the right neighborhood, just immediate right, we can see functional values, that is f of x values, are more than f of x naught. When I call this point x naught, f of x values to the right are more than f of x naught, but whereas for it to become a local maxima, f of x should be less than f of x naught. F of x naught should be the greatest value in the neighborhood. So here f of x naught is the greatest value in the neighborhood. To its right, functional values are much greater than f of x naught. So this cannot qualify to become a local maxima. Let us observe this point. When we look at the left side, f of x values are smaller than f of x naught. F of x values stand smaller than f of x naught. But to the right, the values are all equal to f of x naught. F of x values are all equal to f of x naught. So because of the equality, again this point is not qualified to become a local maxima. Same case here, f of x values to the left of x naught are again equal to f of x naught. So again this doesn't qualify to become a local maxima. Take any point here. To the left and to the right, function values are greater than f of x naught. F of x naught, if I call it y coordinate of this point, to the left and to the right, function values are greater than f of x naught. So this can again not be a local maxima. For local maxima, function value should be smaller than f of x naught. Now let us look at point 8. Function values to the left are smaller than f of x naught, and also function values to the right are smaller than f of x naught. To the right and to the left, both the ways, function values we can see they are smaller than f of x naught. So this qualifies the definition of local maxima. So we have only one point in the entire range from 1 to 10 which qualifies the definition of local maxima, that is 8. So 8 is a point of local maxima. Similarly, we have the definition of local minima. We have the definition of local minima which says a function y is equal to f of x is said to have local minima at a point x equal to x naught if and only if f of x naught is smaller than, in the deleted neighborhood, f of x naught should be smallest value in the neighborhood, f of x naught should be the smallest value, and no other value in the deleted neighborhood should be either equal to f of x naught or it should be less than f of x naught. So f of x naught should be less than f of x for all x belonging to deleted neighborhood of x naught. In such case, we call x naught local minima. Let us look at it by example of a graph. Let us look at the graph of y is equal to sin x from 0 to 2 pi, 0, pi, 2 pi. Now let us see if any point qualifies to be a local minima. Any point here, to the right of this point, y coordinates functional values are more than y coordinate at this point, y coordinates to the right neighborhood are more than y coordinate at that point, which is favorable for being a local minima. But to the left, function values we can see are smaller than f of x naught. F of x is smaller than f of x naught in the left neighborhood. So in the left neighborhood, we have a problem with the definition. In the right neighborhood, it's okay with the definition. So this doesn't qualify to be local minima. If we focus on this point 3 pi by 2, f of x naught, f of 3 pi by 2, we know it is minus 1. In the right neighborhood, function values are more than minus 1, and also in the left neighborhood, function values are more than minus 1. So f of x naught is smaller than f of x for all x belonging to deleted neighborhood, whether it is to the left neighborhood or to the right neighborhood, f of x is greater than minus 1. So we say this point 3 pi by 2 is a local minima. The local minimum and local maximum together are called local extremum. Let us familiarize ourselves with all the terminology. Local maxima plus local minima together, they are called local extremum. Local maxima is also called relative maxima. Whether we say local maxima or relative maxima, it is one and the same. Similarly, whether we say relative minima or local minima, it's one and the same. And the word local extremum is same as relative extremum. So, relative extremum or relative maxima or relative minima correspond to local extremum or local maximum or local minimum respectively. Let us look at another example to identify local maximum and local minimum on a given graph. Let us say I have a graph stretching from 1 let us say this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have a graph stretching from 0 to 10 and this is how the graph looks like. Let us see which point on the curve qualifies to be a local maximum and which point on the curve qualifies to be a local minimum. So, we are starting the graph from 0 to 10. No point in between 0 and 1 is qualified to be local maximum or local minimum. Values to the left are smaller than f of x naught, values to the right are more than f of x naught. So, it is neither a maxima nor a minima. If you observe this point 1, f of x naught is y coordinate at this point at the peak. F of x values are smaller than f of x naught both in the left neighborhood as well as in the right neighborhood. So, f of x naught is more than f of x or f of x is less than f of x naught in the left as well as right neighborhood, that is in the entire deleted neighborhood. F of x is smaller than f of x naught. So, this qualifies to be a local maxima. This point 1 is a local maxima. At 2, though in the left neighborhood functional values are more than f of 2, in the right neighborhood functional values are equal to f of 2 and equality should never come in the definition of local maxima or local minima. So, this does not qualify to be a maxima or minima, and same is the case with 3. This is not qualified to be a maxima or minima. Let us observe f of 4. Function values in the left neighborhood are smaller than f of 4 and also in the right neighborhood are smaller than f of 4. So, the function qualifies to be a local maxima. So, this is also a point of local maxima. Let us observe 5. The function values in the left neighborhood of 5 are more than f of 5 and function values in the right neighborhood of 5 are also more than f of 5, because f of x is more than f of x naught. F of x naught is the least value in the neighborhood, we call it local minima. So, 5 qualifies to be a local minima. Let us look at 6. The left side values are more than f of 6 and right side values are also more than f of 6. So, this point qualifies to be a local minima. So, 6 is also a point of local minima. And 7 we can see we have a local maxima at this point. Left side values and right side values are smaller than f of 7. 8 qualifies to be a local minima. Left side values and right side values are more than f of 8. 9 qualifies to be a local maxima. So, 9 is a maxima, 8 is a local minima, 7 is a local maxima. So, on the entire graph, we have 4 points of local maxima or relative maxima and 3 points of local minima or relative minima. 1, 4, 7 and 9 are points where we have local maximum, are points of local maxima, and 5, 6, 8 are points of local minimum. Let's look at another example. Let's say I have a function whose graph is this way. Let's say I have a graph which stretches from 0 to 5, and this is 1, 2, 3, 4 and 5. Let's say we want to investigate this function for local maxima or minima. From 0 to 1, there is obviously no local maxima or local minima. Functional values to the left are smaller, functional values to the right are larger. Let us observe at 1. At 1 we have some functional value which corresponds to y coordinate at this point. To the left, functional values are smaller than f of 1, and to the right, functional values are more than f of 1. So, one side it is smaller, capable of being a maxima, another side it is functional values are larger, making it to push towards minima. So, effectively it is neither maxima nor minima. Let us observe 2. Functional values to the left are more than f of 2, and function values at right are smaller than f of 2. Y coordinate, we can see the points are below. So, y coordinates at these points are all smaller than f of 2, and y coordinates for all the points to the left are larger than f of 2. So, again this does not qualify to be a local maxima or local minima. At 3, we have points to the left side having y coordinates smaller than f of 3, points to the right side also having y coordinates smaller than f of 3. So, this qualifies to be a local maximum. 3 is a point of local maxima. And at 4, we can see function values to the left are more than f of 4, and to the right also more than f of 4. So, 4 qualifies to be a local minimum. So, we have local maximum at 3 and local minimum at 4. No other point qualifies to be a local maxima or local minima. Then we have a very important theorem which brings in the role of application of derivatives in the discussion of maxima and minima. Local extremum occur only at critical points. Local extremum occur only at critical points. So, be it local maxima or local minima, it occurs only at critical points. Be it local maxima or local minima, if at all it occurs only at critical points. So, it is necessary but not sufficient for us to have a local extremum that the point should be a critical point. Proof of this is very simple. Let us say we are investigating at a point x equal to x naught. Let us focus on derivative at x naught. F dash x naught is equal to limit x tending to x naught f of x minus f of x naught divided by x minus x naught. From the chapter of limits, continuity and differentiability, we know derivative at x naught, it is given by limit x tending to x naught f of x minus f of x naught divided by x minus x naught. Now, as x tends to x naught, we have both right hand limit and left hand limit. When we are evaluating the right hand limit, which is limit x tending to x naught plus f of x minus f of x naught divided by x minus x naught, and when we are evaluating the left hand limit, limit x tending to x naught minus f of x minus f of x naught divided by x minus x naught. Here in the first case, x is more than x naught, so that is denominator is positive. And it has to be a local maxima. In case of a local maxima, be it in the right hand limit or in the left hand limit, f of x should be smaller than f of x naught. So for it to be a local maxima, f of x minus f of x naught should always be a negative number in the neighborhood. F of x minus f of x naught is a negative number, x minus x naught is a positive number. So altogether we are evaluating limit of a negative function, limit of a negative function. And let us look at left hand limit. X minus x naught, x is smaller than x naught, denominator is negative, numerator is also negative because f of x has to be less than f of x naught for a maxima. So numerator is negative, denominator is negative, ratio is positive. We are evaluating limit of a positive function. Now if at all we have maxima at x naught, left hand derivative is limit of a negative function, left hand limit is limit of a positive function, and right hand limit is limit of a negative function. If at all both of them have to be equal, both the limits should be 0 or they will be unequal. So whenever we have a maxima, derivative has to be 0 or the derivative should not exist, which is the qualifying remark to say x naught is critical point. Similarly, for the discussion of minima, if x naught is a point of minima, f of x minus f of x naught is positive, x minus x naught is positive in the right hand limit, f of x minus f of x naught is positive, x minus x naught is negative in the left hand limit. So right hand derivative is limit of a positive function and left hand derivative is limit of a negative function, and for both of them to be equal, they can be equal only for 0, that is when derivative is 0, or they will be unequal. So either the function should not be differentiable or the derivative should be 0 for us to have a minima. So for us to have a local extrema, be it local minima or local maxima, it is essential, it is necessary but not sufficient that the point should be a critical point. Let us look at the discussion by an example. Find, let us look at the discussion by an example. Find local extremum, find all local extremum for f of x is equal to mod x plus sin x, mod x plus sin x in the interval, all the points of local extremum in the interval minus pi to pi. Now local extremum, whenever they occur at critical points, and critical points are the points which belong to domain of the function. Domain of this function is R, mod x is defined on R, sin x is defined on R, and where either the function is non-differentiable or derivative is equal to 0. Now there is only one point of non-differentiability. F of x is equal to mod x plus sin x is not differentiable at 0. So 0 is the only point of non-differentiability. Elsewhere mod x is differentiable and sin x is differentiable, so their sum will always be differentiable. Now derivative is equal to 0. Let us differentiate f dash of x. Derivative of mod x is 1 whenever x is greater than 0, and derivative of mod x is minus 1 whenever x is less than 0. So mod x derivative is 1 for x greater than 0 and mod x derivative is minus 1 for x less than 0, plus sin x derivative is cos x. So f dash of x is equal to 1 plus cos x whenever x is greater than 0 or minus 1 plus cos x whenever x is less than 0. So let us see when this derivative is equal to 0, that is when cos x is equal to minus 1, and cos x is equal to minus 1 it happens nowhere from minus pi to pi. Cos pi is minus 1, but pi is not included as a part of our discussion. Nowhere else 1 plus cos x is 0. Then let us look at f dash of x is equal to minus 1 plus cos x, that is when x less than 0. For this to be 0, cos x has to be equal to 1 and cos x is equal to 1 only at x equal to 0, and again which does not fall into our purview of discussion here. So, there is no point between minus pi to pi where derivative is equal to 0. So, we have only one point where the function is non-differentiable, that is 0. So, 0 is the only point which qualifies to be a local extremum. 0 is the only critical point. Now, let us examine whether we have local extremum at 0 or not. Let us identify the graph of mod x plus sin x. At 0, x is 0 and sin x is 0. So, the graph passes through origin. To the right, x is positive, sin x is positive, and slowly the values start increasing. So, when we move forward along the positive x axis from origin, we will have some positive functional values. And to the left, sin x is negative, mod x is positive, and we know sin x values are smaller than the values of x. We have a very important inequality which says sin x is less than x is less than tan x from 0 to pi by 2. So, modulus of sin x, modulus of x, modulus of tan x, modulus of x will be greater than modulus of sin x from minus pi by 2 to pi by 2. So, because the positive number is more in magnitude than the negative number, to the left side also functional values will be positive. So, we can see f of 0 is the least value, local minima, so which qualifies to be a local extremum. So, there is only one point of local extremum which is x equal to 0. Now, let us see test for local maxima and local minima. We discussed that local maxima and local minima, if at all they occur at critical points, but at the critical point whether a extrema occurs or not. If at all it occurs, whether it is a maxima or a minima, as of now we do not know how to find, and these tests of local maxima and local minima will help us. The first way in which we can test for local maxima and local minima is obviously by graph, which we already discussed when we are defining local maxima and local minima. If in the graph we identify that f of x naught is more than f of x for all x belonging to deleted neighborhood, then we say the point is a local maxima. Or on the graph, if we identify that f of x naught is smaller than all values of f of x in the deleted neighborhood, then we say it is a local minima. If none of them happens, it is neither a minima nor a maxima. Second way to test for local maxima or local minima is first derivative test. It is first derivative test. But first derivative test is applicable only for continuous and differentiable functions. So, whenever we are applying this derivative test, we have to ensure that the function is continuous as well as differentiable at that point. Only then this derivative test is applicable, otherwise not. So, the first derivative test or the second derivative test which we will be discussing is useful only to determine whether a point is local maxima or a local minima when the critical point is critical point because f dash of x is equal to 0, not in the case of non-differentiability. So, while using first derivative test, let us just observe the graph of a function which gives us a local maxima and a local minima. So, this is example of a function which gives us local maxima and a local minima. Local maxima is at a point A and local minima, let us say it is at a point B. Now, if I observe tangent slope in the left neighborhood and tangent slope in the right neighborhood, we can see a tangent with acute angled inclination in the left neighborhood and a tangent with obtuse angled inclination in the right neighborhood. So, derivative at a left side point of A, derivative to the just left side point of A is negative, and derivative to the just right side point of A, derivative to the just left side point is positive, acute angled inclination, and derivative to the just right side point is negative in case of a maxima. So, whenever a maxima occurs at a point A, because f dash of A is 0, then we need to check f dash of A minus, that is derivative to the left side of A, and f dash of A plus, which is derivative to the right side of A. If derivative to the left side of A is positive and derivative to the right side of A is negative, then we can confirm that it is a local maxima. And similarly, for a local minima, just observe the derivative slopes to the left and to the right. Any point to the left of B has its derivative negative. Slope of the tangent here is negative. We have obtuse angled inclination tangent. And to the right, we have a acute angled inclination tangent. So, its slope will be positive. So, derivative to the right is positive. So, derivative to the right is positive, f dash of B plus is positive, and f dash of B minus is negative in case of a minima. So, in case of a local minima, f dash of B minus would come out to be less than 0, and f dash of B plus, that is derivative to the right, will come out to be greater than 0. In that case, say it is a local minima, and in case derivative to the left is positive, f dash of A minus is positive, and derivative to the right is negative, that is a case of local maxima. Brief at a point which is a critical point, because derivative is 0, let us say we are discussing for local maxima and local minima at a critical point A, where f dash of A is equal to 0. Now, let us see the sign of f dash A minus and the sign of f dash A plus. If the sign of f dash A minus is positive and sign of f dash of A plus is negative, that means tangent to the left is acute angled inclination. Let us draw a acute angled inclination line here, and tangent to the right is obtuse angled inclination. So, we can see a peak at the top which corresponds to a maxima. This corresponds to a maxima. Let us say in another case, we find f dash of A minus to be negative and f dash of A plus to be positive. That means f dash of A minus tangent to the left of the point is having obtuse angled inclination, and tangent to the right of the point is having acute angled inclination. So, this we know, we can see here it is a point of minima. And in the case where both of them are negative, in the left side we have a tangent with obtuse angled inclination, and in the right side also we have a tangent with obtuse angled inclination. This leads to a point which is neither maxima nor minima. So, no maxima, no minima. And if we have a point where both left side derivative and right side derivative are positive, so at this point we can see to the left we have acute angled inclination and to the right also we have acute angled inclination. Again, this point does not qualify to be a local maxima or local minima. Such points, they are called under points of inflection. They are called points of inflection. So, we have a local maxima when f dash of a minus is positive and f dash of a plus is negative. We have minima at a critical point A if f dash of a minus is negative and f dash of a plus is positive, and in the case where both of them are same sign, it is neither a maxima nor a minima, they fall under the case of points of inflection. And one more thing we have to be sure, that the first derivative test is applicable only when the function is continuous at the point A. The function has to be continuous and differentiable. First we have to ensure that it is a critical point, f dash a is equal to 0, and then we will apply first derivative test to check whether it is a local maxima or a local minima or a point of inflection. Let us look at 3 examples. Find all the points of local maxima and local minima for the curve y is equal to x cube minus x square. Find all the points of local maxima and minima for the curve y is equal to x cube minus x square. So, to find the points of local maxima and local minima, we need to find all critical points. First step is to find all critical points. There are no critical points because of non-differentiability, because this is a polynomial function and polynomial functions are not differentiable or differentiable on R. And where derivative is 0, 3x square minus 2x is equal to 0. Differentiate y, y dash is 3x square minus 2x equated to 0. We have 2 points, x equal to 0 and x equal to 2 by 3. So, there are only 2 critical points, 0 and 2 by 3. So, let us see whether these critical points are local maxima or local minima. At 0, let us focus on f dash of 0 minus and f dash of 0 plus. F dash of x is what? 3x square minus 2x, x we can take common, 3x minus 2, f dash of x is x into 3x minus 2. F dash of 0 minus, we need to see whether it is positive or negative when x is less than 0. When x is less than 0, this quantity is negative. This quantity is negative. 3x minus 2, when x is less than 0, 3x minus 2 is also negative. X is close to 0. So, this quantity is 0, minus 2 is negative. So, 3x minus 2 is negative and x is negative. Their product is positive. F of 0 minus is positive. And let us look at f dash of 0 plus. X is greater than 0. This quantity is positive. X is greater than 0. This quantity is positive. And x is close to 0. So, 3 into 0 minus 2, this quantity would be negative. So, a positive number into negative number is negative. F dash of 0 plus is negative. So, we can see f dash of 0 minus is positive and f dash of 0 plus is negative. To the left we have a tangent with acute angled inclination, and to the right you have a tangent with obtuse angled inclination, and this qualifies to be a point of maxima. At 2 by 3, f dash of 2 by 3 minus and f dash of 2 by 3 plus is what we need to focus on. When x is less than 2 by 3, 3x minus 2, when x is less than 2 by 3, 3x by 2 would be negative, and x, because x is close to 2 by 3, is positive. So, f dash 2 by 3 minus is x is positive, 2x minus 3 is negative, so their product is negative. So, this is a negative quantity. Let us look at f dash of 2 by 3 plus. F dash of 2 by 3 plus, when x is close to 2 by 3, x is positive. X is more than 2 by 3, so 3x minus 2 is also positive. So their product is positive. We can see derivative to the left hand side is negative, derivative to the right hand side is positive. So one is negative, other is positive, and this qualifies to be a point of minima. This is a point of minima. So we have for this function local maximum at x equal to 0 and local minimum at x equal to 2 by 3. Let us investigate for the function y is equal to x cube for points of local maxima and minima. Now, this is again a differentiable curve. We need to identify all critical points, and critical points will be points where derivative is equal to 0. We will not have any point of non-differentiability in the case of x cube. So, derivative f dash of x is 3x square, and when we equate it to 0, we have only one critical point, which is x equal to 0. So, there is only one critical point, x equal to 0. At this point, we have to check whether it is a maxima or a minima. So, for that, let us observe what is f dash of 0 minus and f dash of 0 plus. F dash of x is 3x square. At a point to the left of 0, slightly smaller than 0, when I substitute here, 3x square would be positive. Irrespective of whether x is negative or positive, because we have x square, it will be positive. And f dash of 0 plus is also positive. Now, to the left, tangent slope is acute, positive, and to the right also tangent slope is positive. So, it is acute angled inclination tangents. So, when both of them are acute angled inclination tangents, it is neither a point of maxima nor a minima. It is called a point of inflection. So, when we draw the graph of x cube and observe, this is how the graph would be. It is a point of inflection at 0. It is neither a point of maxima nor a minima. Then, we have third test of derivatives for maxima and minima, which is second derivative test. Now, if we have a critical point A where f dash of A is 0, that is a critical point not because of non-differentiability but because derivative is 0, and f double dash of A is positive, then we conclude that A is a point of local minima. We conclude that A is a point of local minima, and if f double dash A is less than 0, then we conclude that A is a point of local maxima. A is a point of local maxima. So, if we have a critical point where f dash of A is 0 and f double dash of A turns out to be greater than 0, then A is a point of local minima, and if f double dash of A is less than 0, A is a point of local maxima, and if f double dash of A is equal to 0, this test fails. We will not be in a position to conclude whether it is a maxima or minima or neither maxima nor minima. In that case, we need to revert back to first derivative test and use first derivative test to achieve the result. So, in second derivative test, we check whether a point is critical point or not because of derivative being 0, and then we twice differentiate the function f double dash of A at that particular point. It comes out to be positive, then we say that point is a point of local minima, and if the double derivative comes out to be negative, we say A is a point of local maxima. Let us look at it by a small example, which we already know, that y is equal to sin x at pi by 2 has a local maxima and at 3 pi by 2 has a local minima. Y is equal to sin x at pi by 2 has a local maxima and at 3 pi by 2 has a local minima. Let us confirm it by this test. Y is equal to sin x is the function which we are observing. Let us find the critical points. F dash x equal to 0 implies cos x is equal to 0, and cos x is equal to 0 between 0 to 2 pi at pi by 2 and 3 pi by 2. Cos pi by 2 is 0 and cos 3 pi by 2 is 0. So, we have two critical points because derivative is 0 at these 2 points. Now, let us observe f double dash of x. Differentiating sin x, we got cos x, and differentiating cos x, we would be getting minus sin x. So f double dash of x is minus sin x. Let us observe f double dash of pi by 2. F double dash of pi by 2 is minus sin pi by 2, which is minus 1, which is negative. F double dash of pi by 2 is negative, so we can conclude pi by 2 is a point of maxima. As observed, pi by 2 we got it to be a point of maxima. And let us look at f double dash of 3 pi by 2. F double dash of x is minus sin x. Minus sin 3 pi by 2, sin 3 by 2 is minus 1, minus of minus 1, it is plus 1. So f double dash of 3 pi by 2 is 1, which is positive. So f double dash is positive, indicates this is a point of minima. So one is a point of minima and other is a point of maxima, and that is what we got from the graph as well. So this is how we use the second derivative test. For at any point, if derivative is equal to 0, that we call a critical point. There we have a chance of having a local extremum, either a maxima or a minima. If double dash of a comes out to be positive, we conclude that it is a local minima. If f double dash of a comes out to be negative, we conclude it to be a local maxima. F double dash a positive, minima, f double dash a negative, maxima. If f double dash of a is equal to 0, we cannot draw any conclusion. It is advisable to go back to first derivative test and conclude whether it is a point of local maxima or local minima. Next, a simple concept of global maxima and global minima. It discusses whether a given function has greatest value in an interval or least value in an interval. A function y equal to f of x is said to have a global maximum value or a global maxima at x equal to a or at x equal to x naught if and only if f of x naught is greater than or equal to f of x for all x belonging to I. I is the interval in which we are discussing global maxima or global minima. A function f of y equal to f of x is said to have a global maxima in the interval I at the point x equal to x naught if and only if f of x naught is greater than or equal to f of x for all x belonging to I. So the definition is very important here. A function y is equal to f of x is said to have a global maximum in an interval I at the point x equal to x naught if and only if f of x naught is greater than or equal to f of x for all x belonging to I. Equality symbol is there here, but not in the definition of local maxima. So a point can qualify to be global maxima, not being a local maxima. And similarly, the definition of global minima, a function f of x is said to have a global minima in an interval I at x equal to x naught if and only if f of x naught is less than f of x for all x belonging to I. A function y is equal to f of x is said to have a global minima at the point x is equal to x naught if and only if f of x naught is less than f of x for all x belonging to I. So this is the definition of global maxima and the definition of global minima. Let us see how to use these definitions in determining global maximum value and global minimum value of a function in any given interval. Let us look at an example. Take the graph of y is equal to sin x from 0 to 2 pi. From 0 to 2 pi, in the interval of 0 to 2 pi, let us talk about the function y is equal to sin x. Now, let me observe the function value at pi by 2. We know the function value is 1. Now, f of x for x any point in the interval 0 to 2 pi, f of x we know it will either be smaller than or equal to f of pi by 2. F of pi by 2 is 1. Sin x will always be less than or equal to 1. Equality at pi by 2 in this particular interval 0 to 2 pi, and everywhere else it is a inequality. So, pi by 2 qualifies to be a global maximum. Pi by 2 we can say it is a point of global maximum, or the maximum value is 1. Pi by 2 is called point of global maxima or global maximum, and the maximum value or the global maximum value is 1. Similarly, if you look at the function value at 3 pi by 2, at 3 pi by 2, at 3 pi by 2 function value we know it is minus 1, and f of x is always greater than or equal to minus 1, which is f of 3 pi by 2. So, for all x belonging to 0 to 2 pi, we can say f of x is greater than or equal to f of 3 pi by 2. So, 3 pi by 2 is called a point of global minima or global minimum, and the minimum value is minus 1. So, minus 1 is called global minimum value of the function in the interval 0 to 2 pi, and in the interval 0 to 2 pi the global maximum is at pi by 2, and 3 pi by 2 is the point of global minima. This is how graphically we can determine whether a point is global maxima or global minima.